How are you guys doing? This is Mike Johnson here, and in this video we are going to go over how to determine and find the location of vertical asymptotes of a function. So we're going to entitle this vertical asymptotes. So vertical asymptotes and domains have a very strong correlation. So before I jump into vertical asymptotes, we're going to talk about domains. And specifically, we're going to talk about domains of rational functions. So domains of rational functions. It will only be with rational functions that we will have to worry about, especially at this level of college algebra. For anyone cluing into this video that is not in my course, this is specific to a college algebra section. So this is a college, ooh, that's not good, college algebra section. So again, all math works very, very well. It's all very harmonious. So this will apply to any section of math that you take, but this is specifically geared towards college algebra. So the nomenclature and the words we're going to use are specific towards this course. And this is in the state of Florida. The code for this course in the state of Florida is MAC 1105. So just as an idea, this will be a MAC 1105 college algebra course in the state of Florida. So domains of rational functions, we get back to here. This could be determined. We determine these. Determine domains of rational functions by setting the denominator of the function not equal to 0. Because wherever the denominator of the function equals to 0, we know that function will be undefined at that point. So let us go ahead and look at an example of the following function. Let us look at f of x equals 2 all over x minus 3. And I were to say, what is the domain of this function? We want to identify the domain of this function. So if we want to find the domain of this function, we say, where are all the values of this function going to exist? Where will all values of x, because x corresponds to our domain, what are all values of x that will allow this function to exist? And sometimes it's easier for us to describe where this function does not exist, because there's way more values for x that will allow this function to exist. So in order for us to do that, we are going to set x minus 3 not equal to 0, adding 3 on both sides, so we're going to get x not equal to 3. And clearly, if we were to plug f of 3 in, we would get 2 all over 3 minus 3. This is 2 all over 0, and that would be where this function is undefined. So if we want to describe the domain would be x such that x cannot equal to 3, and this is set notation. And we could also write this in interval notation. So we would start at negative infinity and go to negative 3. We would not include 3, so we have to enclose that with a parentheses. We would unionize that with a value of 3, and then go all the way on to positive infinity. And this would be interval notation. So that's how we would find the domain of this function, very simply just by setting the denominator not equal to 0 and excluding this value. That means the domain can be any other value that we want, any other value of x, as long as it's not 3. So negative 100, negative 0.6, positive 22 thirds, 11, and 17 24ths. Those are all values in the domain that will allow this to exist. So any value that is not equal to 3. So if I were to give you another function, again, this will be another function. I'm going to ask you to find the domain. I'm going to ask you to find the domain of this function. Let's say I give you g of x is equal to 3 all over x squared minus 9. So that's an x squared minus 9. So again, following that same protocol, we know that x squared minus 9 cannot equal to 0. We can go about solving this two different ways. We can factor x squared minus 9 to x plus 3. times x minus 3 not equal to 0, and we could set these two factors independently not equal to 0. So we would have x plus 3 cannot equal to 0 and x minus 3 cannot equal to 0. So x cannot equal to positive 3 and x cannot equal to negative 3. So we have these two values that will not be allowed in our domain. If you didn't want to factor it, you could also solve by adding 9 on both sides. So we'd have x squared cannot equal to a value of 9. But remember, when I take the square root, solving for the value of x, and this should all be under the square on the square, I know that I would have to get x being equal to 2 solutions. So x cannot equal to plus or minus 3. Because remember, negative 3 squared gives you 9, positive 3 squared gives you 9. So no matter which way you go about solving this, you would also have a domain restriction. So at plus or minus 3. So here we solved it by factoring. Here we solved it by just setting this equal to not equal to 0 and then solving. Either way is fine. Writing the domain out, we would have the values of x such that x cannot equal to plus or minus 3. Or we'd write this in interval notation. And a lot of times interval notation can be a little convoluted, but we're going to start off here at negative infinity and go until negative 3. We're going to include negative 3 to positive 3, and then we have to include positive 3 to infinity. So I think actually it's a lot easier to write this in set notation many times because interval notation can sometimes be a little cumbersome. But it's your choice. It's your choice. There's definitely a lot of faculty. There's a lot of people that like to write in interval notation, and a lot of people like to write in set notation. I really don't care either way in my class as long as we understand the difference and we know how to determine them. I'm usually pretty happy. So that's sort of an overview of domains. And now we can see exactly how this relates to vertical asymptotes. So vertical asymptotes are a graphical representation of domains. A graphical representation excuse me, of domains. These describe where the function does not exist or where it is undefined. So we describe where the function does not exist or where it is undefined. So let's go ahead and look at this past value g of x. G of x will be equal to 3 all over x squared minus 9. We said that x cannot equal to plus 3 or minus 3. So if I were to look at a graph here, and I'm just going to draw a quick graph, nothing too perfect, just to give a basic idea of what to expect. We have the horizontal x-axis, the vertical y-axis, and I recognize here that there will be some values, positive 3 and negative 3, that don't exist. So graphically, we would often see on a graphing calculator dotted lines that go down representing the vertical asymptotes. Because we know that x cannot equal to positive 3 and negative 3. These are excluded in our domains. The domain of this function, as we said before, the domain of this function is x such that x cannot equal to plus or minus 3. So now if I asked you, what is the equation of this vertical line, this vertical dotted blue line? We recognize the equation of the blue line will always be a vertical line. The vertical asymptote will always be a vertical line, and this is written in the form of x equaling to a constant, and we clearly see that constant is equal to 3. I should write that in blue. So this will be x equals to 3. This will be the equation of one vertical asymptote. And this vertical asymptote will be x equaling to negative 3. So here we have one vertical asymptote at x equals to positive 3 and another vertical asymptote at x equals to negative 3. I don't have a graphing calculator program on me, but I know when I was an undergrad, I couldn't afford a graphing calculator. I was pretty strapped for cash. So every couple dollars I had usually went to buying gas or buying food. So I was not able to afford a big expensive graphing calculator. But now it's awesome because you can actually go on Google and just search a graphing calculator. So I'm just going to search on Google for a graphing calculator. So, oh, your browser's been upgraded. Wonderful. So we're just going to search graphing calculator. So I've done it once before, and I really like this Desmos one. I've actually searched a couple of them, but I've actually appreciated this one. It tends to articulate the equation really well. I think this is the one I like. Is this the one I like? Let me see. Let me see if that's the one I like. Yeah, I definitely don't like that one. So notice all these different graphing calculators are coming up. Let's see. Do I like this one? Why? Nope, I don't like that one. I think I like this Desmos one, so I'm going to come back here and use this one. So notice here I want to graph the original function that I had, 3 over x squared minus 9, so I'm just going to type 3 divided by x raised to, which was shift 6, the caret, the second power, I'm going to hit over minus 9. And notice here when I graph this, even though we don't see the point 3 and negative 3, doesn't come up with a vertical line here, I promise you that there is a vertical asymptote here at positive 3 at the line x equals to positive 3, and then there's another vertical asymptote here at negative 3. So vertical asymptotes have a strong correlation to domains. So how would I write a vertical asymptote? So a vertical asymptote, I'll just keep writing in blue, can be determined by setting the denominator of a rational function equal to 0. So notice here, in order for us to find a vertical asymptote, we have to set the denominator equal to 0. In order to find the domain, we have to set the denominator not equal to 0. So again, very similar, however, still somewhat different, because here we're going to get an equation of a vertical line. So I will write that in red. So here, this will describe an equation of a vertical line, which is always in the form of x equaling to a constant, where that constant exists as any real number. This is always the equation of a vertical line. So let's go ahead and give an example. So let's do 2 examples. Determine the vertical asymptotes of the following functions. So let's say we had f of x equals to 2x plus 3 all over x minus 2. We'll say g of x equals to 3x squared minus 2x plus 1 all over 4. And h of x equals to x all over x squared minus 5x plus 6. So if you want to go ahead and pause this video and try out these examples, you're more than welcome to. I think that might be a better opportunity for you to see if you've really understood how to determine the vertical asymptotes of rational functions. So hopefully you pause the video and try it out. Now you're back. So again, we're finding the vertical asymptotes. The rules for finding the vertical asymptotes are setting our denominators of our rational functions equal to 0, different than finding our domain, because our domain would restrict this value. It would have to be not equal to 0. So we're just going to add 2 on both sides. So we get the vertical asymptote here will exist at positive 2. So graphically, just a quick graph, I would see down here at positive 2. And if I were to graph this on a graphing calculator, or the equation, it would look something like this. The graph would either have to go up to positive infinity or go down to negative infinity, and it would come down here from positive infinity or come up from negative infinity. So one of those two options. I'm not going to go into what happens here because that's more pre-calculus, calculus related. Maybe a little more college algebra, but for right now we're just going to find the vertical asymptote. So here this will be the vertical asymptote for f of x. Notice over here we're going to follow that same protocol. We're going to set our denominator equal to 0. But hopefully we all recognize that 4 never equals to 0. Therefore, there are no vertical asymptotes. There are no vertical asymptotes because in reality, g of x is a polynomial. And since g of x is a polynomial, we realize the domains of all polynomials are always all real numbers. There's never any breaks or holes, so we don't have to worry about this having a vertical asymptote. This guy will continue from negative infinity to positive infinity. Then lastly over here with h of x, we know in order to find the vertical asymptotes, we have to set x squared minus 5x plus 6 equal to 0 to find the vertical asymptotes, because again they have to be equations of lines. So in order to solve this, we could either use the quadratic formula or factor. I preferably like to factor because it's easier for a lot of times. So we're going to factor this into x minus 3 times x minus 2, still set not equal to 0. So I know x minus 3 equals to 0, and x minus 2 is equal to 0. I think I said prior not equal to 0. We set it equal to 0 to find the vertical asymptotes. And now we add 3 on both sides. So we get x equals to 3. Here we're going to add 2 to both sides. So we get x equals to 2. So here in this rational function, we're going to have two vertical asymptotes, one at 3 and one at 2. So if I just draw a quick graph down here, nothing too exact. Here's 1, here's 2 at 3. I will have something like this. And you're probably going to have to zoom out if you're doing this on your graphing calculator to verify, because I think I'm pretty sure this will give you a upside down curve down here, but it'll be really, really low. I think it's going to be really low. And this will be like this, and this will be like this. I'm pretty sure, but I'm not 100% positive. I'm just trying to do the graph in my head. You know what, we can graph it and we'll check it out. So we'll have x over x squared minus 5x plus 6. So let's go ahead and pull it open on our graph. So I'm just going to delete this. We're going to have x backslash parentheses x raised to the second power over minus 5x plus 6. So notice if we look at this, it looks like it's just going up, but when I zoom out, as I saw, that this will actually have an upside down portion here. So at 2 and 3, there are vertical asymptotes. These graphs get very, very close. They are asymptotically close to the lines x equals to 2 and x equals to 3. But in order to see this, you'd probably have to zoom out on your calculator. So just be cognizant of that. So in this circumstance, you might have to zoom a little bit because it does get really, really close. And I don't know if it would actually show up in your view. It does look like it zooms in really here and close at the value of -10, but you might have to zoom out just to check it out and see exactly what it looks like. So again, you can use your calculator to verify what the graphs look like. However, you never want to substitute the technology for actual knowledge and process. So just be careful about that. The one last bit I want to cover, which some of you may already know, but we have to discuss the difference between removable discontinuities and irremovable discontinuities. So removable discontinuities and irremovable discontinuities. Irremovable discontinuities. So ultimately, these are just fancy terms for this guy is a vertical asymptote. Asymptote. We cannot remove the discontinuity, so it will not be continuous here and here. So this is an irremovable discontinuity. This is also an irremovable discontinuity. We cannot get rid of that discontinuous portion. So over here, however, with removable discontinuities, these are discontinuities we can remove, and these are synonymous with holes. This will be a hole in your graph. So let's go ahead and look at an example. And the example instructions will be determine vertical asymptotes. So I know before in the instructions we said we always want to find vertical asymptotes by setting the denominator equal to 0. Here I'm going to change around the steps slightly. Is that I'm going to say, if possible, factor your numerators and denominators first prior to setting the denominator equal to 0. So we want to do this because if you can cancel out a term, you are actually canceling out or removing a discontinuity. You are removing a discontinuity. So let's look at an example. So let's say I give you f of x is equal to x plus 2 all over x squared plus 5x plus 6. So before I set x squared plus 5x plus 6 equal to 0, I recognize that I can cancel that. I can factor that first. So I'm going to have x plus 2 all over x plus 2 times x plus 3. So I factored those prior. So be careful. Notice here, I recognize that I have an x plus 2 in my numerator and x plus 2 in my denominator. Since I have a common term, I can cancel them. So what I did here is that I removed removable discontinuity. I removed a discontinuity. So before we might have made a mistake and said that x plus 2 gives us a vertical asymptote. In reality, it actually doesn't. It's going to give us a hole in the graph. But this lecture is not focused on removable discontinuities. This one is focused on the irremovable discontinuities or the vertical asymptotes. So I'm not going to labor too much on what this hole looks like. But again, this would be a removable discontinuity. But be careful. When I cancel out a term, these are no longer equal to each other. I can't just say that's 1 all over x plus 3. And I know some faculty, just for sake and purpose, and some people might just say they're equal to. I say that this behaves like, or you can say it's approximately equal. They are equal at every single point, or except at -2, when x equals to -2. These two behave like each other. They behave like each other, except when x equals to -2. So they are very similar except when x equals to -2. With this one at -2, with this original function, we'll have a hole, and this function, we will actually have a solid line. So just be cognizant of that. So now since we simplified, we can go ahead and set that denominator equal to 0 to find the vertical asymptote. So the vertical asymptote can be found by setting x plus 3 equal to 0, subtracting 3 on both sides, and we get x equals to -3. So in this circumstance, even though it looked like we had two vertical asymptotes, because a factor canceled in the numerator and denominator of our rational function, we only have one vertical asymptote, and that's going to be at -3. So if you guys have any questions, please let me know. I hope this lecture helped on how to identify vertical asymptotes of rational functions, and I wish you all the best.